Good morning. So let's start our lecture today. Now, we actually have we have a makeup class on next Tuesday. Okay, next Tuesday during the normal class hour. Okay, so please be punctual in attending that makeup class. We still have something to talk about. So there will be one double lesson makeup class on next Tuesday. So in this lesson, we are going to discuss more about waves, and we will end this lesson slightly early because we want to do the cross evaluation. So today we will end our lesson about 10 to 15 minutes earlier. So we will leave you some time to do the cost evaluation together. Now, so I will share the PowerPoint now. In our previous discussion, we have a state without proof. The expression for sinusoidal waves traveling along a taut string. So this is a string, and the label of the string is the coordinate x. So different x label different position of the string. But the displacement is not given by x. X is just a label. It just gives you an position where you look at. But the displacement is not x. The displacement is a transverse motion, right? It's the up and down motion of the string. And the displacement is given by u. Now, so when the wave passes through the string, different position on the string will have different disturbance. And so u will be a function of x. But at the same time, since the whole wave is moving, okay, so the disturbance at a certain position will also change with time. And so the u, the disturbance, is also a function of time t. So we write u as a function of x and t. X is the position of the string at a certain position. T is an arbitrary time during the travel. So x and t, they are independent of each other. You can choose to look at the string at a particular position and at a particular time. So we write the sinusoidal solution as in this form, u naught cosine kx minus omega t. And we have proven that the constant k is related to the wavelength by this formula. The wavelength, the wave number, the so-called wave number k, is just the reciprocal of the wavelength multiplied by 2 pi. Okay, so that's easy to remember. And the constant omega is a usual angular frequency. The angular frequency is related to the period of the wave by omega equal to 2 pi over t. Okay, where t is a period. Now we also have followed the position of the peak along of a peak along the waves. So after following it for a while, for a time t, the position of the peak advance forward by a distance x, and we are able to find that the velocity of the waves, which is x over t, is given by omega over k. But this expression is not new to you, right? Because we know that omega is 2 pi over t and k is 2 pi over lambda. So if I substitute this these two expressions for omega and k, then I immediately obtain the relation that the velocity of the wave is just given by lambda divided by t. And if I write the frequency f as 1 over t, 1 over the period, then this expression is just a standard, the familiar expression you learned in high school, the velocity of the wave being equal to the frequency multiplied by the wavelength. Okay, so these are the standard things we have learned in the last lesson. Now you may wonder why there's a minus sign here between kx and omega t. Well, there's a minus sign in front of the omega. Now let's discuss about it. Now, in our previous discussion, we follow a peak. We set for the first peak of the wave, we set the argument of the cosine to be equal to 0. Okay, so the guy inside the bracket, k minus omega t, the phase, the total phase is equal to 0. Because we know that when the guy inside the bracket is 0, cosine is maximum. So that corresponds to a maximum or peak on the wave. And that is in fact the first, this is in fact the first peak. So when we follow the motion, when we always set this to be 0, meaning that we follow it motion forward, we find that x and t are related in this manner. X is equal to plus omega over kt. But omega over k, as we say, is the velocity of the waves. So x become vt. Now there's a plus sign here. There's a plus sign here. Because of the minus sign here, if we move the omega t term to the right-hand side, that become a plus sign. So you can see the peak is now moving in the positive x direction. And so the whole waves is also moving in the positive x direction. So a minus sign here before the omega will give you a wave that travel in the positive x direction. That is to the right. Okay. Now, how about if I, instead of putting the minus sign here, I put a plus sign? If I put a plus sign before the omega, what will happen? Now we can still follow the peak, and we set kx plus omega t equal to 0. Okay, the 0 inside the cosine always correspond to a peak. Okay, now we solve for x again. We find that if the sign before the omega is a plus sign, then x become minus omega over kt, or minus vt. And obviously, this expression tells you something. It tells you that the peak is now moving in the negative x direction because there's a negative sign before the velocity. Okay, so the peak is now moving in the negative x direction. Okay, so that corresponds to a waves travel in the negative x direction, and that is to the left. Okay, now there's a rule which allows you to determine whether the wave is traveling to the right or to the left. The rule is simple. You can determine the relative sign of omega and k. The relative sign of omega and k determine the direction of travel of the wave. Now, if the sign before omega and k are opposite, like this, for example, one negative and one positive. Now, for this example, the constant before k is positive. The sign before omega is negative. So one positive, one negative, they are opposite sign. So that corresponding to a wave traveling to the right. And if both omega and k are of the same sign, like for this example, both of omega and k carry a positive sign, then that corresponding to a wave traveling to the left. Okay, so that is easy to remember. If the two quantity, if the omega and k are of opposite sign, that corresponding traveling to the right. If they are of the same sign, corresponding to traveling to the left. Okay. Now you may also add the initial phase if you like. Okay, you may add the phase like this, a positive phase, and a positive phase will corresponding to shifting the curve as a whole to the negative x direction initially. Okay, so imagine when the time t equal to 0. Originally, this should be a cosine curve, but with a positive phase phi, that corresponding to shifting the curve to the negative x direction by the phase phi. And how many periods of shift that corresponding to phi over 2 pi? You have to divide phi by 2 pi and multiply by the wavelength, and you will see how many wavelength does the curve shift. It's easy to remember. For phi equal to say pi over 2, it corresponding to a quarter of a wavelength. If phi is equal to pi, that corresponding half of a wavelength. Okay, so you should at least remember these two special angle. Okay, now but if I use minus phi here and phi is positive, that means I negative initial phase, then the whole wave will be shifted to the right hand side to the positive x direction by initial phase of phi. Okay, so initially at time 0, the wave is not a cosine, but a cosine shifted to the right by a phase of phi. Okay. Now let's see this example. You have two waves here. One wave is kx minus, the cosine is kx minus omega t minus pi, and the other wave, it has inside the bracket minus kx minus omega t. So can you stretch the initial wave pattern, that is a wave pattern at time 0, and state the direction of travels of the two waves? Okay, so can you do it now? Now it may be better if you scratch the cosine curve first. You put time t equal to 0 because you are talking about the initial shape of the waves. So you put time t equal to 0, and what is a curve cosine? Now here we have minus kx minus omega t in the argument, but we also have the sine instead of a cosine. You notice that. So what waves would that correspond to? You just stretch the first, stretch that out. Okay. I give you 4 minutes to do it. Have you got the answer? Who got the answer? Now let me do it together with you. Now we have two waves. The first one is like this. U1 equal to U naught, right? Cosine kx minus omega t minus pi. Now we set the time t equal to 0. So at time t equals 0, it becomes something like this. U naught cosine kx minus pi. Okay. Now first we plot without the pi. Okay. Now this is the diagram. We first plot a curve of cosine kx without the pi. So it looks something like this, right? This is x. This curve, I call it cosine kx with the amplitude u naught. Is that right? This is u. I better extend it to also to the negative x direction because there's a shift now. Now, so there's a phase of minus pi. What would that correspond to? A negative phase will corresponding to shifting the curve to the positive x direction, right? So the whole curve will be shifted to the positive x direction. But by how much? Pi is what? Pi is half of a wavelength or half of a period, right? Do you remember that? We always compare the phase find with 2 pi, then multiply by a period. Okay, pi corresponding, if I put pi here, it corresponds to half of a period. Okay, so that means you shift the wave to the right hand side, or you can equivalent it could be the wavelength. It doesn't matter. You shift the wave to the right by half of the period. So this originally is a maximum. Now, if I shift the whole curve to the right hand side, it becomes a minimum. Is that right? And the maximum will becoming something here. So there is still 0, and this become the minimum. 0 again, but this become the maximum. Okay, this is 0. This is the minimum, and this goes to 0 again. So this is the curve u naught cosine kx minus pi. Okay, does it make sense? You consider this curve shifting by a whole wave, half of a wavelength to the right. Now, in fact, plus pi or minus pi is just give you the same answer, because you imagine shifting this curve to the left by half of a wavelength, you still get this curve, right? So it doesn't matter. You plus sign plus pi or minus pi just give you the same curve. Okay, so this is the curve you got. And if you like, you can convert this curve into a sine. I can write it as if I invert this, it is just u naught cosine pi minus kx, right? It doesn't matter, right? If I invert the two, because cosine a negative value is just a cosine, right? Cosine is an even function. Now, if I consider kx to be in the first quadrant, then this angle is in the second quadrant. Pi minus an angle is in the second quadrant. So when I convert into a sine, there should be a minus sign in front. I better erase it. So when I convert this into a sine, there's a minus sign in front. So it becomes minus u naught sine kx, which is this curve. Okay. Sorry, I got something wrong. Sorry, I got something wrong. It's not this guy. It's cosine, but it's of negative sign. Is this curve? Okay. Now, how about if I have another curve like this? U naught sine minus kx minus omega t. How about this? Now, at time 0, it becomes minus u naught. It becomes minus u naught sine kx, right? So it becomes something like this. The minus sign, the sine curve is something that looks like this, but the minus sign is a curve that looks like this. This is a minus sine curve. Okay, so this is the minus sine curve. Now, what is the direction of travel of this wave? The sign before omega and k are opposite, so it's travel in a positive x direction. For this case, both the sign of omega and k are negative, so they are of the same sign. So that corresponds to wave traveling in a negative x direction. Okay. So is that okay for you? So I save it. And let's continue. Now, what we have discussed is just a special case because we are considering a sinusoidal waves of only one wavelength or equivalently one frequency, right? And that is called a monochromatic waves. Now, the word monochromatic actually have some meaning. You look at the root of the words. You separate them, separate the words into mono and chromatic. Now, the word chromatic, actually the chromatic means color, okay? And the color for light waves corresponding to the frequency. So that means that the frequency. And mono means a single, okay? So we are considered a single color for light and a single, that is a single frequency waves. So that's why we call a single frequency waves a monochromatic waves, okay? And that corresponding to a wave with only one frequency. Now, but don't think that the discussion is restricted, because if you go to the senior study, you find that there is a method called Fourier analysis. An arbitrary vibration, arbitrary waves can be decomposed into the superposition of many sinusoidal waves. So if we learn the mathematical language of a sinusoidal waves, and we vary the wavelength we vary with different frequency, we construct many frequency components, and we add them up together, then we can produce an arbitrary vibration. So the monochromatic wave is actually the basic. When you learn how to solve the wave equation by the monochromatic wave, then you can always superpose monochromatic wave with different frequency to produce an arbitrary vibration or arbitrary waves along the string. Okay, so any waves can be formed by the superposition of monochromatic waves with different frequency. So that is a trick. So that's why we only learn this solution. Okay, because once we learn this solution, we can construct any other solution out of it. Okay. Now we then talk about the kinematics the dynamics of the waves. In the previous discussion, we concerned about the kinematics, how the wave move, but we haven't related the motion of the waves with the force. Now we relate the motion of the waves with the force. And we will derive a equation that describes the motion of the wave in relation to the force. And that is a straightforward application of Newton's second law. Okay, so we are going to apply Newton's second law to derive the wave equation, which describes the motion in relation to the force. Now here we have a monochromatic waves. U equal to U naught cosine kx minus omega t, right? Now this describes the motion of different parts of the string. If x is not the same, if we choose a different x, that means we are looking at a different position. Okay, x can be chosen arbitrarily. For example, if we choose x equal to 0, then we are always looking at the position x equal to 0. We are always looking at the origin to see the wave of the particle there vibrate up and down. If we choose, for example, we can choose another x. If we choose x equal to 1 meter, then we are always looking at the position where x is equal to 1 meter. Okay, looking at another position of the string, then we see the particle vibrate up and down again. So x means we look at different parts of the waves. You can choose different x, and you look at different parts of the waves. Now we would let you see why acceleration is involved in the wave motion. And when we derive the so-called wave equation, we will show you that this acceleration, it needs satisfy Newton's second law. Okay, we will start with Newton's second law and show that this wave motion is in fact the solution of the equation F equal to ma, is a consequence of the Newton's second law F equal to ma. Now we consider a string which is under tension, and the tension tau is the same as the whole string. Now there may be some little bit of variation, but as long as the disturbance of the wave is not much, this disturbance is much smaller than the length of the string, then the tension tau remains almost the same along the whole string. Now this is an approximation, which is not strictly correct, but this is a good approximation. Okay. So this whole string has the same tension, but the angle does vary. If you look at the different part of the string, sometimes the tangent direction is flat, okay, and sometimes on this side the tangent direction is downhill, and on this side the tangent direction is uphill, right? So the angle does vary. The tangent force have a different angle at different position, but the magnitude of the tension force is almost the same along different part of the string. That is our approximation. And we also assume a uniform string of mass mu per unit length. Okay, so this is the mass per unit length, meaning that if you want to find, for example, the total mass of the string, you need to multiply the mu by the total length of the string. Mu L give you the total mass of the string. If you want to find the mass of a small part of the string, for example, I consider a small part of length delta x on the string, then the mass is given by mu multiplied by delta x. So mu, the density multiplied by the length, always give you the mass of that part. Okay. And we assume, as before, the disturbance or the displacement of the string is given by the function u, which is a function of both x, the position, and also the time t. Okay, so these are our assumption. Now we can derive our wave equation. We consider a small segment of the string. The segment extends from x to x plus delta x. Okay, And so the corresponding mass will be the density mu multiplied by delta x. Okay, so this is the part of the string we consider. Okay, and the mass of this part is mu multiplied by this little width delta x. Now, as we say, the tension along the string is tau, but the angle does vary, right? We assume at this moment, we look at the left part of this segment. Now, this segment has two ends, right? The red segment has two ends, the left end and the right end. Now we look at the left end. We assume that at the left end makes an angle. The tangent to the left end of the red part makes an angle theta 1 with the vertical, with the horizontal direction. Now this angle is now below the horizontal direction, right? So the tangent force that acts on this red segment from the left hand side is in this direction. This is a tangent force F1. And this force is actually pulling this part of the string downwards, okay, at an angle theta 1 to the horizontal direction. Is that clear? Now, so this position, the label is x. The tangent force is tau. The magnitude of tension force is tau, and the tension force is now pulling at an angle theta 1 below the horizontal direction. Okay, so how to find the this F1 has a magnitude of tau, but we are interested in the vertical component of the force. Okay, because it's the vertical component that pulls this part of the string up and down. We want to find its vertical acceleration. So we're interested in the vertical component of the force. So in order to resolve the tangent force into the vertical component, we multiply the tau by the angle sine theta. In fact, this should be sine theta 1, right? Sine theta, okay? We skip the subscript for simplicity, actually. So this is multiplied by this angle. Tau multiplied by sine theta is a vertical component. And because it's downwards, right? So there's a negative sign, okay? Now we make an approximation now. We replace the function sine by tangent. We assume this angle to be small enough, right? If the angle theta is small enough, then sine theta, tangent theta, and theta in radian, they are all almost the same. Okay, so we replace the sine theta by the tangent theta, and because that is approximation, we write approximation sign here. Now, why we need to do that? Why don't we just leave it as sine? Because we want to express this tangent in terms of the derivative of u with respect to x. Now, u is a vertical displacement, right? So du dx will be tangential to the curve, will be the tangent of the angle theta 1, right? Du dx is just a tangent theta, okay? Okay, because du dx is a slope of the curve, and the slope of the curve is just a tangent, right? It's just a tangent of the angle theta. Okay, so now we can replace tangent theta by du dx. And be careful, because this angle is vary at the left-hand side, which is at position x. So we should be careful. We are evaluating this du dx at position x, okay, which is just the left-hand side of the segment, okay. Now we should deal with the right-hand side. We do the same for the right-hand side. Now we don't have to do the derivation again because we know everything will be very similar to what we did, except on the right-hand side, now the string is being pulled upwards. So this is a positive sign instead of a negative sign. So F2 refers to this force, and the y component has a positive sign because now the force is pulling the string, this part of the string upwards. And because there's a slight change in angle, Now, on the left-hand side, the angle is theta 1 because the string is curved, right? It's curved. So on the right-hand side, the angle has changed. It's changed to another angle. Let's say the angle is theta 2. So when I evaluate this du dx to find tangent theta, this quantity should not be evaluated at x, but it should be evaluated on the right-hand side because there's a slight change in angle now. So I evaluate the derivative du dx at the new position x plus delta x. Is that clear? Okay. Now, so the magnitude of the force are actually the same. But when we resolve the vertical component, there's a change in angle, right? The left-hand side angle is not the same as the right-hand side, the angle on the right-hand side. So the du dx for the left-hand side is evaluated at x, but the du dx on the right-hand side is evaluated at a slightly different position. Okay, it's evaluated at x plus delta x. Okay, so what would then be the net force? The net force is of course a sum of these two. Okay, we sum up F1 and F2 to find the net force, and I denote the net force by delta Fy. Okay. Now let's consider this subtraction. Now, if both the derivative are evaluated at x, then the subtraction is simply 0. Nothing result, right? But the derivative is now evaluated at a slightly different position. Okay, which means that this quantity is slightly different. So the subtraction is not 0 now. Now, if I consider a function I call small f to be equal to du dx, then the first term will corresponding to the function f evaluated at x plus delta x, while the second term will corresponding to the function f evaluated at x, right? The difference between the function evaluated at x plus delta x and the function evaluated at x can be approximated by the derivative, right? Now, this is just a Taylor series expansion. Do you remember the Taylor series expansion, the first two terms? If you don't remember, I write down now. I better use a notation that makes you remember the Taylor series. Remember when we have a function f and there's a fixed point I call x naught, okay? And suppose now I have a small change in delta x. So what would then be the Taylor series? Now then I will be, I better use this notation. Suppose I'm making a Taylor series about a fixed point. The fixed point is called x naught. What is the Taylor series? This is the first term, right? What is the second term? The second term is s prime, the first derivative, evaluated x naught, divided by 1 factorial, x minus x naught. Is that right? Now I ignore the higher order. Okay. Now this is the difference between x and x naught, which I can call it as delta x. Is that right? Now, so this will become what? This will become x naught plus delta x. I can write that x naught plus delta x. Is that right? Now, so if I do it like this, I can rewrite this formula at x f x naught plus delta x equal to fx naught plus f prime x naught delta x. Is that right? Now, if I move this term to the left-hand side, this exactly become this, right? Fx naught plus delta x minus fx naught, which is equal to approximately equal to the derivative of f at the fixed point multiplied by delta x. Okay, so this is actually the Taylor series expansion up to the first order in the derivative. Okay, now so that's why we can write this difference as a derivative of the function f df dx. So I differentiate the du dx once more. Now my du dx is f, right? So I differentiate once more, multiply by this delta x. Now, so when I differentiate this once more, it becomes the second derivative. Is that right? So it becomes tau, the second derivative of u multiplied by delta x. And that is the net force acting on the part of the string. Now, Newton's second law is the net force equal to the mass times the vertical acceleration, right? So I get the vertical force. The vertical force is this. The mass is mu delta x, and the acceleration is of course a second derivative of u with respect to t. Okay, this is the acceleration. So now I just write down Newton's second law. The net force being equal to the mass of that segment multiplied by the acceleration. And if I cancel the delta x on both sides, then I obtain the so-called wave equation. The wave equation states that the tau, the tension multiplied by d square u dx square, is equal to mu, the density multiplied by d square u dt square. Now, you should note that although the two terms look very similar, they're actually very different. The term on the left-hand side is a derivative of u with respect to the position. The position is x. And the right-hand side is the derivative of u with respect to time. Okay, so the derivatives are different, although they are both the second derivative. But the left-hand side is a derivative of with respect to x, while the right-hand side is a derivative with respect to time t. And x and t are independent of each other. Okay. Now this is possible because u is both a function of x and t are independent of each other. Okay, because you can look at the wave at a different position and at a different time. X and t can be chosen independently. So in mathematics, if you learn higher mathematics, higher calculus, then this kind of derivative is commonly called a partial derivative. And I would make a slight change in notation. Instead of writing this as a full derivative, I now write this as a so-called partial derivative. Now this symbol is like a 6, but inverted, laterally inverted 6, all right? This is called a partial derivative. What's the meaning of that? It is a derivative in a usual sense, but when I do the derivative with respect to x, I keep the time t as a constant. I treat the time t just like a constant. I don't differentiate it. I take it as an independent constant, which is independent of what I'm doing now. Okay, so that is the meaning of the partial derivative. Again, for the time t, when I take the derivative of u with respect to time t, I use the partial derivative now, which means that I do the differentiation of u with respect to time t while keeping the position x constant. Okay, so when I do this, when I take the derivative with respect to time t, I just treat the x as a constant, which is independent of t. That is what the derivative means. So there's only a slight change in notation. And with this slight change in notation, we can now write down the wave equation. So the wave equation can be written as this. Okay. Now, there's a kind of pronunciation that you should learn. The derivative of u with respect to x, the partial derivative, is commonly called round u round x. Okay, this is the partial derivative with respect to time t. It is called round u round t. So the symbol, which is an inverted, laterally inverted 6, is commonly called round. Okay, so you can call it, this derivative round u round x, and you can call this derivative round u round t. Just like when it's full derivative, you call it du dx, right? Now you replace the d with the u, with the round. The round is a partial derivative. So here we got the wave equation. The wave equation is look like this, right? Now this is nothing but just the application of Newton's second law. We just apply Newton's second law to a small segment on the string, and we arrive at this equation. Okay. Now, but this is a partial differential equation, which means that it involves derivative of different quantity with respect to different independent variable. The right-hand side is derivative with respect to time. The left-hand side is derivative with respect to space. Okay, so that's why it is called a partial differential equation. Now, we have studied this solution, monochromatic wave pattern, right? At the beginning of the course, when we talk about the kinematics of the waves, we just state this solution. Now we have the dynamic. We now relate it to the force. So in order to for this solution to be a solution to the problem, we have to show that this expression in it satisfies the wave equation. We have to show this solution is a solution to the wave equation. It satisfies the wave equation, right? So how do we show this? How do we show the monochromatic wave solution satisfies the solution? Well, the easiest way is to substitute the solution back to the equation to see under what condition can it be satisfied? Can the wave equation be satisfied, right? Now the proof is not difficult. It's quite simple, but we should take care of the partial derivative. Now let me write the shorthand. We write the shorthand C as a quantity kx minus omega t. Now, so we take derivative of the u now. U is equal to u naught cosine C, right? Where C is this guy. So we apply the chain rule, the usual chain rule for partial for derivative. The chain rule tells us that if I differentiate with respect to x, and the C is a function of x, then the chain rule tells us that we should differentiate the cosine with respect to C first. And then we multiply the derivative of C with respect to x. Is that right? This is the usual chain rule. But now we apply this chain rule to the partial derivative. And C is just by definition this guy. Now, so round cosine C round C is just minus sine C, right? And round C round x is just the derivative of this quantity of this guy with respect to x. But as I say, when I do the partial derivative of x, the time t is maintained at constant, is regarded as a constant. So the derivative of t with respect to x is 0 because t is independent of x. Okay, so my differentiation only goes to this term. When I differentiate it x by x, then I got 1. And I only get an additional factor of k. So this is round C round x. I only get a factor of k here. Okay. Now, so eventually what I got is minus u naught k sine kx minus omega t. Now, how about if I differentiate again to find a second derivative? Now, the rule is simple. You can see from this calculation that the rule of differentiation of doing the partial differential is simple. Whenever I do a derivative, I turn the sine into cosine or cosine into a minus sign. Now for the second derivative now, we turn the sine into a cosine. And because we have the chain rule always contains the term round C round x, and that will give me an additional factor of k. So now when I do the second derivative, I got 2k. So the sine become a cosine, and now we have k squared. Okay, and the minus sign is still there. Right? So this is the answer for the second derivative of u with respect to x. So I got round square u round x squared. Okay. And how about the derivative with respect to time? Again, we write the same. When we do the time derivative, we apply the chain rule again. We differentiate the cosine with respect to cut c and multiply by the derivative of cut c with respect to t. This is the same as before. Derivative of cosine is minus sine. When I differentiate the cut c with respect to time t, the x is kept at constant. Now we are doing derivative with respect to time. So x is independent of time. So I treat it as constant. So the derivative is 0. And the derivative of time x only on the second term, which only gives me a factor of minus omega. So what I have is now a factor of minus omega at the end. So the two minus sign cancel, and I got the answer as u naught sine kx minus omega t omega. Now, how about if I do the differentiation once more to find the second derivative? The sine become a cosine, is that right? And when I apply the chain rule, I differentiate the cut c, I get a factor of minus omega. So there's another factor of minus omega coming out. So together with this omega, I have omega squared and with a minus sign. Okay. So each time you do the differentiation in time, you just convert the cosine into minus sign or sine into cosine and pull out a factor of minus omega. Okay. Now, when we compare the second derivative in space, which is like this, with the second derivative with respect to time, which is this, we can see that they actually satisfy. The u actually satisfy the wave equation, because when we put the two function back to the wave equation, we find that the cosine factor will cancel on both sides. Both sides contain the cosine function, which means that they can be canceled. If they can be canceled, that means the two sides can be satisfied for all time t and all position x. Okay. Now we involve not only time, but we also involve position. And the canceling of the factor cosine means the wave equation can be satisfied for all time and all position. Okay. So that means the solution works. That means this factor is in fact a solution to the wave equation. But there's a condition. In order for the two sides to be equal, these two constants must be equal. The u naught also cancel on both sides, but the constant tau multiplied by k squared must be equal to the right hand side, which is the constant mu multiplied by omega squared, right? So we got tau multiplied by k squared equal to mu multiplied by omega squared. And this equation will give you the ratio of omega over k. But omega over k is a wave speed. We have discussed before, right? Now we express the wave speed in terms of tau and mu, which is the physical property of the string. We now find that the velocity of the waves is given by square root tau over mu. Okay, we just rearrange the term such that omega over k on one side, and we take the square root on both sides. We got the wave speed at square root tau over mu. Now, what is the meaning of that? What is the meaning of doing that? Now, the meaning of doing that, this monochromatic wave is indeed a solution to the wave equation. It can propagate. It means it can propagate along the string. But there's a condition. The condition is that the wave speed of propagation is defined by the properties, the physical properties of the medium. That is, it is determined, the wave speed is determined by the tension and the density of the medium. So the tension tau and the density, the linear density mu, together they determine how fast the wave can travel on the string. Okay. Now, because this is a constant anyway, so we may like to convert this ratio mu over tau, which I put now on the right-hand side together with the second derivative in t, I may now put this constant mu over tau at 1 over v squared. So that becomes the standard wave equation now. Okay. Now in our discussion, we always refer to a taut string, right? That is what we assumed in our previous discussion. So tau and mu corresponding to the tension and the density of the string. But now we write the wave. We now rewrite the wave equation in terms of the general velocity. Okay, and it happens that when we discuss about any other kinds of linear waves, we always obtain this equation, in which the wave speed is always given by a term of 1 over v squared that goes together with the second derivative of u with respect to t. Okay, so this becomes the general wave equation. For other kinds of waves, the v is no longer given by tau over mu square root. You may consider other kinds of wave, for example, sound wave. The sound wave has a wave speed determined by air pressure and air density. And for other kinds of waves, like for example, water waves, it may be determined by the water depth or some other kinds of property. So every kind of wave have a different physical property that determine the wave speed. Okay, but when we are talking about linear wave motion, we always will obtain this general wave equation in terms of v. Okay, so this equation is not confined to a taut string, but it is a general wave equation that applies to all linear wave motion. Okay, you may see other example in your textbook, and in this course we will also discuss another example, and that is sound wave. Okay, we will discuss it later, perhaps in the next lesson, and or maybe in the makeup class next week. Now, we better stop here for